Now it's time to talk about action potentials in greater depth. As you can see here, we started a resting potential of negative 50 millivolts and a threshold at about negative 30 millivolts. The first stimulus that a cell experiences is called a graded potential. Graded potentials are changes in membrane potential that vary in size as opposed to being all or none. They also decrease over time. The magnitude of a graded potential is determined by the strength of the stimulus. Once threshold is reached, our neuron is going to depolarize and the permeability to sodium goes up. This increased permeability to sodium is due to the activation gate of the voltage-gated sodium channel opening, allowing sodium to dump into the cell. At about 45 millivolts, the inactivation gate of sodium closes, preventing sodium from entering the cell. Simultaneously, the potassium voltage-gated channels are open, allowing potassium to leave the cell. This is called repolarization, and the membrane potential begins to decrease back towards its resting state. Once threshold is reached again, the voltage-gated sodium channel is reset. However, potassium sluggishly closes, which causes the cell membrane potential to dip below its resting state. This is called hyperpolarization. Once the potassium gates are closed, the cell returns to its normal resting membrane potential. Let's break down the previous slide into small chunks. This slide shows two pictures, one of the voltage-gated sodium channel and one that shows the cell's membrane potential. It's important to note the two different gates that are located on the sodium voltage-gated channel. As we have learned before, the activation gates are closed until the cell reaches threshold. Until then, sodium cannot enter the cell. Once we have reached threshold, the activation gates open and this allows sodium to pour into the cell. Pay attention to the graph on the right. Notice that as sodium continues to enter the cell, the membrane potential is changing. In this example, at positive 30 millivolts, the inactivation gate of sodium closes and sodium can no longer enter the cell. Additionally, the activation gates of potassium are opened and potassium now leaves the cell. As potassium leaves the cell repolarizes. At threshold, both the sodium activation and inactivation gate reset. Now it's time to talk about the two periods associated with an action potential, the absolute and relative refractory periods. The absolute refractory period starts when the sodium voltage-gated channel is open to when it is closed. It is important to note that the relative refractory period starts when the sodium gates reset. During the absolute refractory period, a cell cannot be stimulated no matter how great the stimulus is applied. This is due to the inactivation gates being closed. A good way to remember the difference between the two periods is to remember that there absolutely cannot be another action potential during the absolute refractory period. The relative refractory period begins when the sodium gates have reset. A cell can create another action potential, but recall that the potassium channels are still open. For another action potential to occur, the stimulus would have to be greater than it normally would at resting state. Again, this is due to the activation gates of potassium sluggishly closing.